Today we're going to add in to our integration stuff, natural log, exponential, and basic trig integration stuff. So before we get into that, I know we've done some trickier U-sub problems. So what I want you guys to do is just do a real quick refresher on how to do these two problems. I'm going to work one of them on the left, and then I'll post on Canvas the worked out on the right. But I want you to pause the video, give this a try. See if you can figure this one out on your own, because it'll really help you out before you get to the rest of the stuff later today. So I know typically we have told you with U substitution you want to look for an expression and its derivative or a slight modification of it nearby, or when you're selecting U, you want to look for something that's kind of inside a radical or a parentheses or some kind of grouping technique here. So for this particular problem, I see that x plus 6 is inside the radical, and I have x dx on the outside. Because x plus 6 is inside the radical, I'm going to say that that's equal to u. So I'm going to say let u equals x plus, x plus 6. Okay, so that means du is simply just, well, in this case, dx, because the derivative of x is 1, but then times dx. So that helps me take care of this guy right here, but I need to figure out a way to rewrite and take care of the x. So instead, what I'm going to do is I'm going to think about the fact that, well, if u is equal to x plus 6, well, then if I just subtract 6 from both sides, u minus 6 is equal to x. Okay, so now I can rewrite my integral, and I have u to the 1/2, so u to the 1/2. I still have du for dx, but for x right here, I need to replace that with u minus 6 and then dx. So I know that's kind of maybe slightly out of order of how it looks up here, but I always start with what's ever on the inside, so u to the 1/2. So u to the 1/2. To take care of the x, you've got to do u minus 6, and then the dx is just du. Oh, I didn't write that. I wrote dx. My bad. du. Okay? Now to integrate this, again, you guys are like, whoa, there's some grouping going on here. There's the radical, like what? Do I do a u sub of a u sub? No, we don't do that. What we're going to go ahead and do is just distribute u to the 1/2 to both terms. So this is going to become u to the 3/2 minus 6u to the 1/2 du. And now I can do a real simple reverse power rule. U to the 3/2 is going to become 2/5 u to the 5/2 minus, we'll go in steps here because we've got a scalar out front, so 6 times 2/3 u to the 3/2 plus c. This stays the same, so 2/5 u to the 5/2 minus 2/3 of 6 is 4, so 4 u to the 3/2 plus c, and then remember u was actually x plus 6, so I'm going to replace both of those and make that 2/5 x plus 6 to the 5/2 minus 4 x plus 6 to the 3/2, 3/2 plus c. Okay? Again, I will have the worked out version of the problem on the right here on Canvas. It's going to look a lot like the problem that we just did, but this is kind of a quick recap of our tricky U-sub problems that you've done over the past few days. Okay, again, this is 4.6 in your textbook for those of you paying attention, following along. Some of these examples aren't actually going to be from your textbook. They're a little bit extra, or I think I may have pulled them from an old book, but you can always have some extra. Never a problem. Okay, so before we get into that, do you remember how to take the derivative of the natural log of the absolute value of x? Hopefully we recognize that this is the same thing. There should be a box. Yeah, there it is. As 1 over x. Okay. And then the derivative of the natural log of u is just 1 over u times u prime, or u prime over u. Okay. So this is how we take the derivative. But that was a couple units ago. Now we are learning how to take the antiderivative. So we're going to go the other direction. So then the log rule for integration, if u is some differentiable function of x, okay, the first one I've got here is that the antiderivative of 1 over x dx is equal to natural log of the absolute value of x plus c. Now, when we take the derivative, the absolute value goes away, but when we take the integral of 1 over x, the absolute value comes back. which it just makes sense. Whatever you do to go one direction, you have to do the exact opposite to go backwards. So the derivative, or the antiderivative of 1 over x dx is natural log of x plus c. At the same time, if we were to have this in terms of u, okay, the antiderivative of 1 over u du is equal to the natural log of the absolute value of u plus c. These are two rules that you are going to want to have memorized. Write them down on your stuff you must know cold, formula chart, all that good stuff. Make sure you know this, okay? So let's do some practice problems here. I've got the antiderivative of 2 over x dx. Well, I know how the rule works when I have 1 over x dx, but now I have a 2. No big deal. All I'm going to do is treat that 2 like a scalar multiple, because it is. So make this 2 times the integral of 1 over x dx. Okay? I know that the antiderivative of 1 over x is the natural log of the absolute value, so this becomes 2 times the natural log of the absolute value of x plus c. Not so shabby so far, right? Let's try another one. So now I've got 1 over 4x minus 1 dx. This one's a bit more complicated because I can't do a real simple scalar multiple type thing. I can't just take out a 4. I've got a 4x minus 1 in my denominator. So this is going to be more along the lines of 1 over u prime times u prime du. Okay, so if I do that, I'm going to try to identify what u is equal to, and in this case, it's simplest to go with whatever's in the denominator. So I'm going to say let u equal 4x minus 1. So du is equal to 4 dx. Now, again, and as we've seen in the past, if there's not a 4 in the problem out here, what can we do? What do we do with this 4? Okay, all I need is dx, but I have a 4 dx. So I'm going to multiply both sides by 1/4, make this 1/4 du is equal to dx. So then I go to my rewrite step here, and then I've got the integral. Instead of 1 over 4x minus 1, I've got 1 over u, and then instead of just writing du, I've got to write 1/4 du, so I'm going to put that 1/4 out front, du. Okay? So then this is going to be, now remember, if you wanted to, you could write that as du over u or 1 over u times du. I don't have a preference. You do you. Haha. Get it? You do you? No. All right. 1/4. The antiderivative of 1 over u is the natural log of u, absolute value of u, plus c. 1/4 natural log of 4x minus 1 plus c. Okay? Hopefully that wasn't too shabby. Okay, now this next problem, let's see. Find the area of the region bounded by the graph of y equals x over x squared plus 1, the x-axis, and the line x equals 3. So this is not a that's not an indefinite integral like we've had in the past. This is a definite integral. Okay, so we want to go from the x-axis and the line x equals 3. So I know I'm going to go from 0 to 3, x over x squared plus 1 dx. Okay, so let's think about this here. It looks like, because I have a fraction here, and let's see, I've got two expressions within my fraction. I've got the numerator and I've got my denominator, and if I look at my denominator of x squared plus 1, if I were to take the derivative of this, that would be a 2x, which I have an x dx right here. I don't have a 2, but I can pretty easily make that work for what I need here. So I'm going to say let u equal x squared plus 1, so du is equal to 2x dx, but again, I just need x dx, so I'm going to make that 1/2 du is equal to x dx, which is what I need. Now, remember back to another video we did, I think it was 4.5 u sub day 2. Whenever I rewrite a definite integral in terms of u, my original bounds are in terms of x, so my new bounds need to be in terms of u. Okay, so let's find our new bounds here. Okay, my original lower bound was 0, okay, but now u is equal to x squared plus 1, so u is going to be 0 squared plus 1, so u is equal to 1 for my new lower bound, and then my upper bound is going to be 3 squared plus 1. Oh, I forgot. Well, u. So u is equal to 3 squared, which is 9 plus 1, so 10. So now when I go to rewrite this, I've got the integral. This is just, well, this guy is 1/2 du, so 1/2 du over u. Again, you could write this as 1/2 the integral of u, of 1 over u du if you would prefer it that way. Again, I don't care which way you do it, just make sure you get it right. Right? And then I need my bounds. Now, I don't want to use my original bounds because those are in terms of x. I need to use my bounds in terms of u. So 1 to 10, 1 to 10. Okay? Antiderivative of du over u is 1/2 natural log of the absolute value of u from 1 to 10. And the nice thing about the fact that this is a definite integral and that it has bounds is I don't have to bring an expression for x back in for u because I've already rewritten my bounds in terms of u. So I'm going to have 1/2 natural log of 10 minus 1/2 natural log absolute value of 1. Hopefully by now we all know that the absolute value, the natural log of 1 is a big fat 0. So we end up with 1/2 natural log absolute value of 10, which is just 10. So you could write it as natural log, like 1/2 natural log of 10. You might see it in your textbook as the natural log of root 10. Those are the same thing, just using your natural log rewrite properties. So either one is fine. Just want to make sure you can recognize between the two of them. Okay? All right, let's keep going. Okay, so with these, without formally writing the u sub, see how quickly you can integrate these. Okay, so some people need to do the formal u sub every single time. And honestly, that's okay. If you are that person, I'm totally fine with it. You need to show your work. But that's not everybody. Some of us can easily identify like, oh, this is u in the denominator and du up front, so I can just go ahead and do the u. I can essentially do the u sub in my head without actually formally doing the u sub. So I want you to pause the video and give these a try. Try to do these in your head. Again, if that's just too much of a struggle for you and you would prefer to write it out, that's okay. This is just one of those things that you can try to do to save yourself a little bit of time. So this guy right here is going to be my u. This is du. So then it's just the natural log of the absolute value of x squared plus c, where u was equal to x squared plus x cubed plus x. I think I kept saying x squared. I meant x cubed. Okay. This one, the denominator is u. The derivative is secant squared. So natural log of the absolute value tangent of x plus c. Pretty quick. Pretty simple. Okay. Now this one's going to be a little bit trickier because u is supposed to be 2x plus 2, and I have an x plus 1, which is very similar, but I'm missing the 1/2. So what you could do, if you wanted to, before you actually formally integrate it, is to go ahead and make that a 2x plus 2 up top, like multiply everything by 2 in the numerator, but whatever you do, if you multiply by a 2 in the numerator, you have to effectively cancel that out at the same time, because otherwise you have changed the value of your original statement. So for this one, they've multiplied the top by 2, but then at the same time multiplied by 1/2, because those two processes would cancel each other out. It's essentially multiplying by a form of 1, just like we do when we need to combine our fractions. We multiply by a form of 1 so that we have common denominators and things like that. Okay, so then now that it looks like a prettier format, this just becomes 1/2 the natural log of x squared plus 2x plus c. Again, same thing with this one. I was hoping to have a 3 in the numerator. If my denominator is 3x plus 2, there's not a 3, but I could put it there. But if I put it there in the numerator, I need to also put a 1/3 in my denominator, or a 1/3 out front, so that way those are effectively canceling each other out. Okay, and this becomes 1/3 natural log of 3x plus 2 plus c. Again, if this is a little bit more than your brain can handle right now, you would prefer to do the formal u sub, write it all out, perfectly fine. Okay, we'll get you to this point. We're all still learning and growing at this point in our time, in our lives. Okay, all right, let's try another one. So x squared plus x plus 1 over x squared plus 1 dx. So I'm going to try to do what I've done in the past with the natural log, but oh gosh, if I set u is equal to x squared plus 1, the derivative is 2x, but I don't have I have an x, but I have an x squared up top. So that process isn't going to work. So what else could we possibly do here? Well, I know that x squared goes into x squared. So I'm going to do, I think the title of what we're going to do. Yeah, using long division before integrating. I know that it's everyone's absolute favorite. So I'm going to go ahead and divide this top expression by the denominator and see if I can make life a little bit easier. So I've got x squared plus 1 on the outside. X squared plus x plus 1. Now, if you are looking at this like long division, what on earth is she talking about? Go back to Khan Academy, Prof. Rob Bob, look up in either Algebra 2 or Pre-Cal, polynomial long division. Okay, that is what we're doing. I can't remember if we would have already done this earlier this year. I don't think we have, maybe with some differentiation, but it doesn't come up a whole lot. So if you are confused by just the process of long division, go back and look up those videos and then come back to this. It'll help make a little bit more sense. Okay, so x squared goes into x squared one time. So then I multiply the 1 by both of these terms. So x squared plus 1, and I'm going to subtract. And then these two things cancel out. The x comes back down. The 1 minus 1 cancels out. So x is all that I have left. So essentially, this integral can be rewritten after I've done long division into the integral of 1 plus x over x squared plus 1 with respect to x. Okay? Again, I used long division to go from this guy up here down to this one. Okay, there's no way for me to integrate this as is. I can't use natural log properties. I can't do anything else. So I have to use long division, and then with that long division, okay, this is my remainder. And remember, we always write the remainder over our original denominator. So then I can rewrite this whole expression as 1 plus x over x squared plus 1 dx. Okay, and then to do the integral process is a lot simpler, because now the antiderivative of 1 is just x plus this guy right here is very similar to the integrals we did on the last page. This is going to be 1/2 natural log of x squared plus 1 inside an absolute value plus c. Okay, again, I was hoping to have a 2x out front, but you can put it there. So if you put a 2x here and just multiply by 1/2, then it becomes 1/2 natural log of x squared plus 1. Okay, let's try. Let's see. Do I have another one of those that might help us out here? Let's see. I don't. Let me add in another. Actually, I'm going to have another one posted on here. Well, I'll write one out real quick. I feel like we might need a little bit more long division practice. So let's say I have the integral of x cubed minus 6x minus 20 over x plus 5 with respect to x, or dx. Okay, so again, the denominator is x plus 5, but the derivative of that is just 1, and I have x. Oh man, I have a lot of stuff in the numerator that's not helping me out here. So I'm going to go ahead and use long division. X plus 5 going into x cubed plus, now I don't have an x squared term, but when I do long division I need a space holder, so 0 x squared minus 6x minus 20, because I need to have all of my powers of x accounted for. Okay, so then I look for x going into x squared, into x cubed. That goes in x squared times, so x squared times x, x cubed, x squared times 5 plus 5x squared. Subtract. Those two things cancel out. 0x squared minus 5x squared becomes minus 5x squared, and I bring down minus 6x. So then x into negative 5x squared goes in minus 5x times, so negative 5x times x, negative 5x squared. Negative 5x times 5 is minus 25x. Okay, I subtract those. These two cancel out. Negative 6x minus negative 25x is going to be positive 19x. Remember, when you subtract a negative, it becomes positive. So plus 19x, and then bring down the minus 20. Okay, so then x into 19x goes in 19 times. So 19 times x, 19x. 19 times 5 is positive 95. I'm going to subtract those again, then this cancels out. 20 minus 95 is going to give me negative 115. So then my new integral, or my integral, can be rewritten as x squared minus 5x plus 19 minus 115 over x plus 5 dx. Simple, simple, simple integration, natural log integration. So this is going to become x cubed over 3 minus 5x squared over 2 plus 19x minus, now I would prefer to have a, no, I don't need a 2, okay, so minus 115 natural log absolute value of x plus 5 plus c. Okay, again, that was just another version or another round of using long division before you can do your natural log properties. Okay, let's keep going, see what else we got on our notes for the day. Evaluate each definite integral. So I'm going to give you some definite integrals coming up here, just to make sure that, because we're using e now instead of natural log, so we're going to throw in some trig and some exponential functions and just make sure that we're all still on the same page. Okay, so I've got, let's see, from -1 to 0, e to the x, cosine e to the x dx. Well, I see two real expressions here, e to the x and then e to the x inside the cosine. So I'm going to say let u equal e to the x. So then du is equal to e to the x dx. That takes care of that, takes care of that, takes care of that. So then I would just rewrite cosine u du. Okay, but because this is a definite integral, I need some new bounds. So then my new lower bound, it was -1, so I'm going to have e to the, well, hang on, I forgot u. U equals e to the -1. So my new lower bound is just e to the -1 or 1 over e. My upper bound is u equals e to the 0, so that's just going to be a 1. Okay, so when I go to rewrite, I'm going to have the integral from 1 over e to 1 of the cosine of u du. Did I get everything? Yep, I think I did. Antiderivative of cosine is sine, so I've got sine of u from 1 over e to 1. So this just becomes the sine of 1 minus the sine of 1 over e. I mean, if you wanted to type that into your calculator, you could, but assuming you didn't have a calculator, this would be a perfectly acceptable answer. Sine of u minus sine of 1, oh, not sine of u, sine of 1 minus sine of 1 over e. Okay? Let's see, find, oh, that's not a definite integral, so I'd find each definite integral. All right, so 1 over x natural log of x dx. Ooh. Well, here I'm going to think about it for a minute. If you need to, go ahead and pause the video, try it on your own, see if you got something, and then come back. So I'm already back because, well, I didn't go anywhere, but what I'm going to do is I'm going to say let u is equal to just the natural log of x. Okay, and the reason for that is because du is equal to 1 over x dx. Well, natural log is in the denominator, that's okay, but then 1 over x dx, oh, that's nearby, because you can think of this as the integral of 1 over x times 1 over natural log of x dx. Okay, remember, all this is being multiplied. So then when I rewrite this, I've got the integral of, let's see, 1 over natural log, so u is going to go in the denominator, so 1 over u, and then 1 over x dx was du, so then this times du. Well, I know that the antiderivative of 1 over u du is natural log of the absolute value of u plus c, but in this case, u was the natural log of x, so I've got natural log of the absolute value of the natural log of x plus c. Ooh, natural log inside a natural log. It's getting real, people. Let's keep going. Antiderivative of tangent. Well, I don't think we've done these yet, so I don't think I have that one memorized. I know sine and cosine pretty well, but I don't have any idea what the antiderivative of tangent is. Because I don't know anything that would give me, like, I don't think there's anything that I can take the derivative of and just get tangent by itself. So what I want to think about is, well, let me go back to pre-cal for just a second and remember that I had some trig identities. Oh, I could rewrite tangent. Tangent is the same thing as the sine of x over the cosine of x, right? Since those are the same thing, like tangent of x, sine of x over cosine of x, I haven't I've changed how it looks, but I haven't changed the value. So now I want to look for the derivative and like an expression and its derivative nearby. Well, it's helpful to do, like, if I look in my denominator here, I've got cosine of x. Well, the derivative of cosine is negative sine, which, yes, I have sine, not negative. That's an easy fix, okay? But if I did that the other way, like if I were to say u was equal to sine of x, well, then the derivative would be in the denominator, and I don't want to have du in my denominator. I need to have du up top, okay? So I'm going to say, in this case, let u equal cosine x, du is equal to negative sine of x dx, which is both in the numerator like I want. I don't have a negative, so I'm going to make that negative du is equal to the sine of x dx. Okay, hopefully everybody's following so far. So then when I go to rewrite, okay, I've got the integral. I'm going to go ahead and have a negative out front because du is negative. I'm going to have, let's see, so u is in my denominator because cosine's in the denominator. So u, and then sine of x dx is the same thing as du. So I have negative du over u, which is negative natural log absolute value of u plus c, or negative natural log of cosine of x plus c. Well, I'll be dang. That didn't turn out so bad after all. So the antiderivative of tangent is negative natural log of cosine of x plus c. Cool. We already knew sine and cosine going into this point, but now we've learned tangent. Cotangent is going to work in a very similar fashion along with the other two. So these are the ones that you need to make sure that you have memorized. Okay? So we already know the antiderivative of sine and the antiderivative of cosine. Okay, we've done those before. We've just discovered that the antiderivative of tangent is negative natural log of the cosine of u. Since cotangent is the reciprocal, it makes perfect sense that the antiderivative of cotangent would be natural log of the sine of u plus c. Okay, now it takes a little bit more trig identities to solve these other two, so I'm just going to give you those. You are welcome to look up the proof for those on your own. I mean, feel free. I'm not going to stop you, but we're not going to go through that formal process right now for the sake of time. Okay, so make sure you have these memorized as well at some point. Perfect quick quiz Wednesday material right here, and then make sure you put these on that stuff you must know cold chart, because you need to make sure you know these right away. Backup plan for tangent and cotangent is to go ahead and do the natural log process by rewriting them, blah blah blah, but it makes your life a whole lot easier if you just have these memorized, okay? Just like a lot of the other stuff in our class. All right, so back to exponential real quick. What if I had the integral of e to the 3x plus 1 dx? I feel like we've done one pretty similar to this one before, but let's just power through this real quick. I'm going to say let u is equal to 3x plus 1, so that means du is equal to 3 dx. I don't have a 3, so 1/3 du is equal to dx. rewrite, and I end up with 1/3 integral e to the u du. So 1/3 e to the u plus c, 1/3 e to the 3x plus 1 plus c. Ah, that wasn't so bad. Not sure why that was in the midst of all of this other trig stuff, but you know what? It's cool. It's fine. It's good practice. Oh, here's another one. Antiderivative of 5x e to the negative x squared dx. I'm hoping by now you guys are kind of easily recognizing what u is supposed to be versus what the du equivalent would be. So in this case, when I see my expression e to something, basically the something is going to be u. Okay, so let u equal negative x squared. So that means du is equal to negative 2x dx. Okay, well, I have x dx. I want x dx, but I also would prefer a 5, not this negative 2. So let's take care of the 2 first. Make that negative 1/2 du is equal to x dx. Basically, I divided it to the other side, so I have x dx, which is exactly what I want. But then I have this 5 right here that I need to account for. So really, if I just multiply both of these by a 5, then I'm good to go. I've got negative 5/2 du is equal to 5x dx. Ah, perfect. 5x dx, e to the u, boom, done. So rewrite, I'm going to have, so I've got negative 5/2 e to the u du. Let me double check. So negative 5/2 du takes care of 5x dx, 5x dx, and then e to the u takes care of e to the negative x squared. Yep, I think we're good. So negative 5/2 e to the u plus c, so negative 5/2 e to the negative x squared plus c. And again, to always check your work, remember, you can just go back and take the derivative and make sure you end up with the exact same thing that you started with inside the integral. Okay, I don't know if we've mentioned this yet. Inside here, this is called your integrand. This is your integral. This is your integrand. Okay, makes sense? So if you wanted to make sure that this turns into the correct integrand, take the derivative. You should get the same thing. If you don't, either you took the derivative wrong or you took the integral wrong. Go back and check your work. Okay, a couple more of these. Ooh, e to the 1 over x squared. And then sine of x e to the cosine x. Oh, so we're mixing the trig with the e to the x here. So this is a great opportunity for you to pause the video, try these on your own, and then come back. When I see this, I pretty quickly recognize, so e to the something. Usually that something is my u. So I'm going to say let u equal 1 over x, or x to the negative 1. So that means du is equal to negative 1 over x squared, or negative x to the negative 2. You can write that either way. I kind of like this way because look, 1 over x squared, ooh, right here. Remember, this is the same thing as the integral of e to the 1 over x times 1 over x squared times dx. Okay, it's just that since they're multiplied, you can just put it in the numerator. Okay, so now, but I don't want the negative, so I'm going to move that over. So I'll have negative du is equal to 1 over x squared. So when I go to rewrite for this one, I'm going to have the integral of e to the u du with a negative out front. Because du, oh wait, that should be dx right there, my bad. Oh, I don't have that on any of these. Silly Murphin. There you go, dx. Those should all have a dx. 1 over x squared dx. That looks a little wonky. I want you to make sure that you recognize this is 1 over x squared and then times dx in the numerator. Dx always, 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 always has to go into the numerator. And this is not a minus sign. This is just, I ran out of room. Okay. So negative e to the u du, this is negative e to the u plus c, so negative e to the 1 over x plus c. Okay? So let's do this next one, sine of x times e to the cosine of x. I'm going to say let u equals cosine of x. So then du is negative sine of x dx. Negative du is equal to the sine of x dx. Rewrite. I'm going to have the integral of e to the u. Sine x dx is actually going to be negative du. So this is negative e to the u plus c. So negative e to the cosine of x plus c. Okay? Couple more examples here, and then we'll be done with this video. It's kind of long. That's okay. Evaluate each definite integral. Okay, so this is using a lot of the same processes that we've already done so far today. I'm going to work these out and have the answers posted on Canvas because we've already done some with area and some with e to the x. So I'll have these worked out, but I want you to just try these on your own. I'm not going to spend time in the video to do these because I think they're pretty straightforward, and they are also in your textbook if you need the actual explanation of these. Okay, so let's see what else we got. This one I am going to do because this one's a little bit different, okay? Why does this one seem a little bit different to you guys, other than the fact that it has trig? I think we're stuck at, oh, it's got trig. Well, we're going to use a trig identity on this one to make our lives a tiny, tiny bit easier, okay? So 1 plus tangent squared x, I can't really do my typical u sub for this one because I don't have the derivative of this anywhere nearby, okay? So I don't want to start out by saying, oh, let's do a u sub. It's actually going to make it far more complicated than you ever intended it to be. So, but what I do know from back in my trig identity days in pre-cal, my absolute favorite unit in pre-cal, I'm sure it was yours as well, 1 plus tangent squared of x is a Pythagorean identity, and that's the same thing as secant squared, okay? 1 plus tangent squared x equals secant squared x. If you don't believe me, go back and check your old pre-cal notes. I promise it's there. You would have learned it last year from, whoever. So I'm going to rewrite this 0 to pi over 4 square root of, instead of 1 plus tangent squared, I'm going to make that secant squared of x with respect to x. Okay, well, the square root of something squared, well, that's super handy. That becomes from 0 to pi over 4 of just the secant of x dx. Oh, not bad. Now, secant, we didn't actually formally prove that one, but we already wrote it down earlier. The antiderivative of secant is the natural log of the absolute value of secant x plus tangent of x from 0 to pi over 4. And so then using first fundamental theorem, I just plug in my numbers here, natural log. The secant of pi over 4 is root 2. The tangent of pi over 4 is 1 minus natural log. The secant of 0 is 1 plus the tangent of 0 is 0. So this becomes natural log of root 2 plus 1. Natural log of 1 is 0, so it's just natural log of the absolute value. Well, I can drop the absolute value because I've got root 2 plus 1. So this just becomes boom. I can either keep it as absolute value, that's fine. I can't get rid of the parentheses though. If I were to drop the parentheses, that'd be the natural log of 2 and then plus the quantity 1. I want the natural log of the quantity root 2 plus 1. So please be careful about when you take out your absolute values. Okay? Alrighty, so I think I've got one more. Oh yeah, find the average value of tangent on the interval from 0 to pi over 4. So this is when we're doing our trig integration, but we're also using the average value theorem, which we haven't seen in a while. Remember, average value theorem is f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, it's been a bit since we've done that, so probably a good time for you to go back and refresh that if you don't remember that one. So basically, I'm just going to try to find what's the average value of f of x. So what's the average value of tangent from 0 to pi over 4? So f of c is going to be 1 over pi over 4 minus 0 from 0 to pi over 4 tangent of x dx. So 1 over pi over 4. The antiderivative of tangent we learned this morning, or today, this afternoon, depending on, we learned it today. I don't know when you're watching this video. Maybe it's in the evening. I don't know your life. Whatever. Okay? Negative natural log of the absolute value of cosine of x plus c. Oh, not plus c. From 0 to pi over 4. 1 over pi over 4 right here, guys. That's the same thing as 4 over pi with the negative out front. So I'm going to go ahead and just do that. And then I've got the natural log of cosine. Well, cosine of pi over 4 is root 2 over 2 minus the natural log. Now, I know you're probably thinking, like, wait, what about that negative? Do I distribute that? I already factored out the negative, so I can still use first fundamental theorem with my negatives like normal. Natural log of the cosine of 0, which is 1. So then natural log of 1 we know is 0. So then the average value of tangent of x on 0 to pi over, wow. One more. Pi over 4 is negative 4 over pi times the natural log of root 2 over 2. I dropped the absolute value here because it's a positive number that I plugged on the inside, so we're good to go. Okay? All right, so that was quite a bit that we did in our notes today. We did natural log integration. We had e to the x. We had some trig. We also had long division in there. As always, Prof. Rob Bob, Khan Academy, Calc Chat, Calc View, all great resources for you to make sure that you understand what's going on.